This is lab 3. And basically, in this lab, there are two parts. And part 1 was analyzing the motion of a star using computational code to determine the mass of a black hole. And so for me, my mass ended up being 1.13 times 10 to the 34th. And the second part is using the mass of the black hole found in part 1, so this mass, to help determine the initial velocity of a spaceship to get it close enough to the black hole without it crashing, but still be able to leave the system. And this is a glimpse into what my answers were. So this is the fundamental physics principles that I ended up utilizing, and so I used Newton's second law, which states that F net is equal to change of momentum, and so change of momentum can get changed into this form, which is d dt times momentum's vector, and then that times p hat, and then that turns into these two equations, which are the F net parallel and perpendicular components. And I also utilized gravitational force in my code, so since the gravitation, according to Newton's law of gravitation, F is equal to g times mass 1 times mass 2 over their distance squared over times r hat, and then which is also, since F net is equal to dp dt, it's also equal to those things. And then here I just moved it around to get mass 2, or in my case, the mass of the black hole. And so this is the glow script model for the part 1. And basically the initial conditions, you can see the gravitational constant, the mass of the star that was given to me, and then the delta t time. And so basically this calculation over here is going to allow me to find the velocity at every time stamp, because it's going to be changing in a circular orbit. That's not constant. That doesn't have a constant radius. Okay, so here is my glow script model, and basically here is the initial and final velocities, here is the definition of momentum, so mass times velocity, and I did that for final and initial, and change in velocity and momentum over here. And I also, important thing, I set the F net to change momentum, which is also found here, which is change in momentum for change in time. And then I found the parallel component of change in momentum by using p hat and d mag p dt. And I used these equations to create a formula over here. And so basically be this over this times that. And then the parallel component of F net, which is the parallel component of the change in momentum. So I set that equal to that. And then over here, I did the perpendicular component of F net, which I found over here as well. And then so the mass of a black hole at the given timestamps was basically over here. And so it's the magnitude of F net times the magnitude of the star's position times the magnitude of the star's position. So basically that's squared, and then over g times this the mass of the star. And I made it print over here like at every timestamp to be able to find like the average of all of them, which would give me the mass of the black hole. And so over here, this is what my orbit ended up looking like. And it also gave me like a list of all these. So there was like 1.33, 1.31, 1 point whatever. And there was like a ton of them over here. And I put that into an Excel document and found the average of all of them. And it gave me 1.31 E34 for the mass of the black hole. And here is the F net component. So the F net, which is 9.093 times 10 to the 28th. And then the parallel component of that is 2.19 times 10 to the 28th. And F net, the perpendicular component, was 8.813 times 10 to the 28th. And basically, if you use Pythagorean theorem, you'll be able to find F net. Okay, so this is part 2 of the lab, and so I used the mass from part 1 in this whole code, and that was 1.31 times 10 to the 34th, and these were constants which I did not change. And then getting over here are the equations to find the initial speed and velocity of the planet, and then over here was the initial speed and velocity of the spaceship, which I had to do like trial and error to see what the values were, so that the planet doesn't like crash into, oh, not the planet, the ship doesn't crash into anything. And so this was also like part of the code. This is until 65, and then this was beyond that. So over here, the planet was the system, and it was acting on the black hole in the spaceship. So I also, that's over here, and then I used Newton's law of gravitation to find F net on the planet. And then over here was the spaceship acting on the black hole on the planet, and I also used the same process of using Newton's law of gravitation to find the F net on the ship. And then so basically I did all of this to figure out the motion of the system over a period of time, which is like this, using net force. Here was my result after multiple trial and errors, and the spaceship was able to leave. So yay. And then, okay, so here were errors and limitations that I thought were actually a part of my whole lab. So I think I made some approximations, like the simulation and reality are very different. So in reality, there could be other forces that have influence on the system. And that kind of goes alongside with my assumptions, actually, because I assumed that there were no other outside forces acting on the systems. And then there could have been errors made with accuracy, since I used trial and error to find all these velocities. And there could have possibly been more precise velocities that could be closer to the black hole than what I had over here. And so these were the discussion questions that I tackled. And so one of them was, how does net force and its parallel perpendicular components differ from the rate of change of momentum and its component? So mathematically, and like their equations, since F net is equal to the change of momentum times change of momentum over time, so equation-wise they're the same. But finding the change of momentum is easier because you just need to know the system's change in velocity. But when you use F net, you need to know like the individual outside factors that are like exerting a force on the system. So that's much harder to find than the velocity changing. And then what initial velocity does the spaceship need to have to orbit around the black hole? This was done through multiple trial and errors, and basically I got the speed to be negative 0.003 times 10 to the 7th in the x direction, and the y direction I got it to be 9.8 times e to the 6th in the y direction. And yeah, thank you.